In this presentation, we will be addressing transportation mode selection by Caterpillar dealers in Latin America. We are Team 10, comprised of 3 seniors and 2 juniors, and I am Katie Jansen. Before we delve into our recommendations, I will begin with a case overview. The problem we are aiming to solve is effective transportation selection. Caterpillar is a large-scale company dedicated to maintaining its reputation of efficiency and being a world leader in customer support. In order to achieve the high service levels they target, Caterpillar must find a way to efficiently determine the most cost-effective mode of transportation while also minimizing lead time and holding costs. In places like Latin America, where distribution follows a hub-and-spoke model, balancing these trade-offs can be especially challenging. Our intended solution aims to find the most cost-effective transportation option from the distribution center in Miami to the hub, and from the hub to each of the given stores. In this way, we will be able to streamline the current decision process while keeping cost efficiency and service level attainment at the top priority.
To address this problem, we created an Excel solver model that would find the optimal transportation route for a particular part from the distribution center to the hub, and from the hub to a specific store. In using this model, a dealer would input the part number and store number, and would receive back information on the most effective shipping solution as well as alternative solutions. First, we'll take a look at the parameters included: transportation cost and lead time. From the DC to the hub, per unit transportation cost was calculated as a given rate multiplied by the part weight. From the hub to a store, transportation cost depended on both part weight and store location. Lead times were constant for every transportation mode except for surface transportation from hub to a store, so this value is looked up. Our first constraint in the model is demand time, which ensures that lead time is less than or equal to the days until stockout. This constraint ensures that customer demand can be met on time. Our calculation of days until stockout will be discussed in detail later. Additional constraints in this model make decision variables binary and ensure that only one mode of transportation is selected for transport between the DC and the hub, and between the hub and the store. The decision variables in our model are binary variables that indicate whether or not a mode of transportation should be used between the DC and the hub, and between the hub and the store. As such, there are 4 variables: air or surface for each of the 2 legs of the journey. Finally, our objective function is to minimize cost. Total cost is broken down into transportation cost and carrying cost, with transportation cost equal to the sum product of per unit transportation cost and decision variables, and carrying cost equal to daily carrying cost times the days until stockout less lead time. These are multiplied by the EOQ, since we assume that all products would be ordered in their economic order quantity. This is an example of the output a dealer would receive, using Part 1 and Store 86. We can see that the most effective shipping solution is surface transportation, with a lead time of 54 days and a total cost of $4.29. This model, however, is not without limitations. The solver model optimizes the route for one product at a time and cannot be used to optimize transportation for multiple items shipped together. Another limitation is that our model assumes products will always be ordered at their economic order quantity, though this may not be the best option. Finally, this model was built with static inventory levels, but when it is used, these levels will be changing frequently.
But how effective is the solution given in the model compared to the alternatives? In order to analyze all of the transportation options, we conducted the same methodology to create 4 models that cover the 4 combinations of potential transportation choices that our solver could generate. Based on this data, we calculated the costs and lead times that each transportation section would require. We also calculated the service level by dividing the part price by the part price plus the holding cost incurred given the lead time generated by the transportation combination solution. From this information, we can see how the different transportation choices change our 3 main KPIs: cost, lead time, and service level. In this particular example, we can see how the solution in the bottom right-hand corner is the most cost-effective and should be the transportation plan chosen by the dealer. By integrating this feature into our model, dealers can understand how the most effective solution was chosen, compare and contrast the importance of key KPIs, and discontinue to consider transportation options that are not deemed feasible due to the company's constraints.
Next, we move on to some recommendations. First, regarding the time value of transportation mode, we took into account the days until stockout and the lead time. We calculated the days until stockout by adding the total inventory on hand and on order, and then dividing it by the average items per order. We then multiplied this figure by days between each order, which was easily calculated by dividing 365 days by the given value of total order lines. By calculating the days until stockout, we were able to determine the time frame in which the product would need to be delivered to prevent any disruptions in service. To ensure this, we then compared the days until stockout to the lead time for each mode of transportation and had the model give us a mode of transportation with an accurate timetable. Next, concerning the cost, there would be no difference between a full or partial truckload, due to the cost being determined by weight and not by mileage, as seen in the data given. This allows for less restrictions on when products can be ordered and the quantity of which they are ordered in. Next, regarding frequency, the model explained before should be run at different frequencies depending on how often orders are placed by customers. There is no need to run the program often if orders are only being placed for a part less than once a month. The median frequency per year of all the stores is 12. That being said, if a part is ordered less than 12 times a year, then it is only necessary to run the program once a month. If the part is being ordered more than 12 times a year, it is recommended to be run once a week to keep up with possible demand changes.
From the model we created and explained earlier in this presentation, it is clear that for some parts the optimal transportation will have changed from one mode to another. With change to an existing system like our new model creates, we feel it is important to stress communication throughout the impacted parties. Communication can help express and explain a proper timeline to order parts and keep everyone informed. Noting the changes in days until stockout and lead time necessary for each part as the modes of transportation changes is vital. Another recommendation to the dealers is to have ample safety stock to cover possible delays due to new transportation methods. With this recommendation, there is a chance that dealerships will have excess inventory as some parts may come quicker with the change in transportation modes. This excess inventory may add an extra expense of holding the inventory that will soon be offset by the savings of the new transportation model. With these recommendations, the disruption to service should be minimal. As previously stated, the new model will lead to some parts changing transportation modes. With that understood, there is the potential for a large quantity of parts to change modes, impacting how the network constraints are managed. As I mentioned earlier, ensuring enough safety stock for parts that changed modes of transportation may be the best way to smooth the transition to the new model in terms of the dealers. With this new model, we don't foresee products switching transportation modes often. We assume that parts would be ordered at the economic ordering quantity, or EOQ. This would eliminate the possibility of parts switching modes every single time it gets ordered, unless a part was needed under emergency circumstances in which the air mode of transportation would be used. After the transition to the new model, parts should be ordered using the same transportation modes, not affecting the constraints of the network.
Our model can easily be applied to Caterpillar operations worldwide. However, in order to do so, there needs to be slight changes to current parameters used as inputs in the model. These parameters include the units used, such as if a currency changes from US dollars or the weight changes from kilometers. In addition, store data will need to be updated as new shipping methods are available that will have different lead times and costs than the current analyzed shipping methods. Finally, new SKU data will need to be used in order to ensure that all parts have accurate cost, demand forecasted, target service level, and other up-to-date parameters. After developing our model, we recognize the risk that dealers may not be as excited or interested in adopting our model as we are. However, we believe that we can make dealer adoption more successful if we can stress that the model will only be utilized to help improve their current operations. We can stress that the model will increase their current efficiency as it is easy to use and allows them to make quicker decisions by utilizing parameters that they likely already know. In addition, the model will save them money by allowing them to ship parts in a more efficient way by analyzing both transportation costs and carrying costs. Finally, the model will be fairly transparent, allowing them to see the decision-making criteria we utilized. The transparency of our model will help Caterpillar's decision-making process. It will allow Caterpillar to make better inventory management decisions because it takes into account carrying costs when making its recommendations. In addition, future parameters could be used, such as available warehouse space, to further aid in the decision-making process. Finally, it will help provide summary statistics organization-wide to help Caterpillar's business strategies. The model also aids in transportation selection. It accurately shows a breakdown of different available transportation methods, and it makes it easy to compare the specifics of each method. Finally, it allows clear criteria for evaluating different transportation options that can help make transportation selection more uniform enterprise-wide.